This video is connected to the November 6th remote class, in which we will be focusing on raster processing. So raster, as opposed to vector that we've always learned, is not modeling an object. We're not modeling a point, a line or a polygon. We are modeling space, geographic space. And so the world doesn't look like polygons or points, but rather the world breaks itself up into a series of grid cells, where each grid cell represents a different value. So if you're following along in the raster intro folder, I'm going to drag in county boundaries first, just so we can prime the data set to Lancaster, Pennsylvania. Might be an area you're familiar with, just west of us. What's going on here? Why can't I see my boundary? There we go. It's just being all silly. And then I'm going to drag in two things. I'm going to drag in a raster here that you can see in the table, or the contents is sort of blue and white squares. It looks like a grid cell pattern. And so if you drag it in, and we'll drag in elevation as well, these are the two, build the pyramids. Turn elevation off at first. So these are two raster grid cells. And I want to walk through each of them for about 5 to 7 minutes, just to sort of understand how it's different and what it's trying to do. Because at first they just sort of look like messes of color. And, if you don't have some context about what they're trying to show you, it can be a little bit unclear. So first, let's look at land cover, but let's mess around and make this land cover like a little bit easier on the eyes. So maybe for the 5 values you have here, maybe right-click urban and, pick like a gray, so it'll be more like developed, city or urban style area. And then come on to agricultural, grab that one, maybe give that like a light yellow like farmland. Come to forest and shrub, pick a green. Come to water, and pick a blue. And other, you can just make that sort of like a pink. We don't really need to know what that is. It's just some random area here. So what you can visually see, what we're looking at here is different land cover in Lancaster. And immediately, right, hearing that different land cover, you should see that it's not really going to be something that's attached to an object. How would you put land cover on an object? That doesn't really make any sense, right? Would it be a parcel? But my parcel of land in the home I own might have a house, which would be urban land cover, and I might have sort of tree cover, which would be forest. I might be on a farm that is farmland but has some forest on it and a river running through it, right? They're not really objects. They are sort of space. And so if you zoom in, and I recommend zooming in on an area that has multiple colors, because that type of area will really let you see what we're dealing with at a very close geography. And so if you keep zooming in, you can see what looks like a mess of color from the farther extent is really the entire world broken apart into thousands upon thousands of grid cells, like a piece of graph paper laid over the world, like a photograph with its pixels. Except in a photograph or a computer, each pixel has a color, has a value. It tells you sort of, what to see with your eyes, so they register a color and you see a picture. But here, the pixels or the cells tell you a value. This is forest. This is urban. This is agricultural. So a couple things. Let's right-click it and go to its properties. The main thing I want you to do when you do that is to come to source. Immediately you'll see it's a raster. But the most important thing is to come here to the raster information, because this is going to hold a couple of really key pieces of information that anytime you have a raster data set, you're going to want to analyze and understand to help you contextualize. So, rows and columns, I'm sure you can figure that out. That's just the total number of grid cells. If you were to multiply one by the other, you would get how many grid cells there actually are. And you can see this is an enormous number right here, right? 2,400 across almost, and 2,200, sorry, 2,200 across, 2,400 across and 2,200 sort of up and down. That many different grid cells, each one representing the land cover. So once you know how many there are, your next question should be, well, how big are they? Because that's an important component of raster, is that every single cell is the same size. It is a critical analytical piece of raster that I'll show you how to fix in place so that once you start creating new rasters, you don't wind up in a place where some rasters are one size and some rasters are another, and it's difficult for them to add together. But the size of them will always be here in cell X and cell Y. Anytime you see a number, you should say, well, 100 what? Bing, bada, boom, right? Whatever the vertical units are, 100 feet. So we have this many cells that are 100 feet by 100 feet, right? So that's a fairly good size that lets me get sort of a picture of land cover without getting too granular. The only other thing to sort of know is this type, this pixel type. And you'll see this, it says unsigned character. We'll see what that means in sort of a second when we actually open the attribute table. But that's the basic thing you want to know with the raster, right? How big it is and sort of how big each of the cells are. How big of a geographic area are we covering? The next thing I want you to do is I want you to open the attribute table. Now, notice the values are here, right? Urban, agricultural, forest and shrub, water and wetlands, and other. All 5 values are here. Now, we just learned that there were, millions of cells. 2, 3, 4 million cells with that value that we had there. Yet I only have 5 records. And so immediately this should help you realize that the structure of raster is also different. Notice, too, in each row, it's not simply a character that corresponds to a land cover. There's also something that tells you a value and a count. And I'm going to select the urban row so that this all will finally fall into place. Every single pixel, all 481,000 of them, that represents urban land cover processes together, is treated in the same row in the attribute table. So all urban land cover, if you were to run a raster operation, would run the same process, would run simultaneously. It's in the same family, it's in the same zone. All forest and shrub, all 594,523 of them would be the same in their land cover. And even more important than that is this thing here that says value. And in the next video, when we actually run a few basic tools, you'll see why value is so important. Urban land cover, agricultural land cover, water, wetlands, forest and shrub, that's for you and me. That's for our eyes to see, to help us visualize and understand what we're looking at. But when we actually run the tools of raster, the mathematical processing operations, urban's not a thing that can be added, right? It's not a linear value. But 1 is. You can't add urban to forest and shrub, but you could add 1 to 3. And so value becomes important, as we'll see, because this is what we'll process. When we start running operations on this, trying to maybe call out only agricultural land or combine this with another raster, we need to know what value means more so than we need to know what land cover means. Let's compare this to the other raster we have called elevation. Now, elevation's a little different. For one, it seems to have more of a stretched value here. For another, I can't actually access the attribute table. Let's open or right-click and go to its properties to try to see a little bit more about why that might be the case. And see that when you come to raster information, the number of grid cells are the same, the cell size is the same, but it's a different pixel type. It's a floating point. What that means is that what we're looking at here is a grid that's actually not telling me a stand-in character that means a land use, right? 1 equals urban, 2 equals agricultural. But this is actually telling me a true numeric value. Each grid cell here tells me the elevation in feet, right? The feet above sea level. And I can zoom in and see the millions upon millions of pixels. I now know the land cover. I know where the valleys are, where the ravines, where the mountains. This is called a linear or a continuous raster. So the first one we saw is often called nominal, right? In name only. It's where the values are standing in for some character-based value. So 1 is urban, 2 is agricultural. This is linear or continuous, right? Where you could actually do mathematical operations. You could add one thing to another. You know, if you're at 500 feet elevation and I'm at 100 feet, you are 5 times higher than I am, right? It's on a continuous linear scale. There's another kind that we'll learn in a second called ordinal. You know, I don't want to get into what an ordinal is, but these are the two big ones that you'll see: linear and continuous, nominal, or character-based. Let's click on elevation and just quickly come up to raster appearance so we can see how we can mess with the symbology. Well, cool, like before, we can do transparency, which is really important for raster when you overlay it on other pieces of data. But more important is this symbology. And if I were to come here and pick stretch, which literally means stretch from the lowest value to the highest value, I get the ability to also start to pick some colors. So I don't have to rely on this sort of data set. I could take this comical one, you know, which is probably better for stretching elevations in areas where you have high snow top mountains and such. And I could do that. I could sort of make it look like, you know, I've got my low river fern valleys here and my high craggy peaks and such, and, you know, maybe be a little bit visually better for my eyes. Or I could come and maybe try to find like a brown scale, you know, something like this where I could scale it. You know, or maybe even go from light to high on something like this. You know, you'll figure it out, whatever's sort of best for you. But again, you're visualizing the elevation of the land right here, and you're shading it and trying to effectively tell yourself that what you're looking at is low points, high points, and everything that is in between. So why, when I'm looking at a linear raster or a continuous raster, why can't I see, and I'm just looking for that one symbology I had that I sort of like to goof around with this. Why can't I see the attribute table? And the reason you can't see the attribute table is because the way attributes are handled, as we mentioned here, is that each unique value represents its own row. So 1 would all be in one row. How many unique values do you think there are for elevation? Because elevation incorporates a decimal, meaning that 1174.6 is a different value than 1174.5. Extrapolate that across the million or so potential values, and it would crash the computer if you opened the attribute table and looked at suddenly 5 million lines. So that's the only reason you can't see it. The values are there. I could zoom into something if I wanted and click on it, right? And it would pop up and tell me, hey, I'm 334 feet, right? That's my elevation. I could come right down to you and click, I'm 241 feet. So just important to remember that they have values even though you can't see the attribute table. So that's the basics of raster, right? You know, you have either these characters or these integers that stand in for characters representing a nominal value, or you have these linear and continuous rasters that are stretching from a low to a high point. So in the next video, I'll start to show you how to process these rasters, right? If you want to add them or query them or run some basic tools on them. And I'll define those tools using sort of the same terminology we did in vector to help you memorize them. And there'll be some very basic ones to get you started.